All right, let's dive into one of the most fascinating parts of the periodic table, the D and F block elements. We're talking about the metals that give our world color, magnetism, and so much more. Seriously, they're kind of like the superstars of the elements, and today we're going to pull back the curtain and see what makes them tick.
So, have you ever really stopped to think about it? What makes a gemstone sparkle with such a deep, brilliant color? Or, what's the actual magic that makes a magnet stick to your fridge? It feels like magic, but I promise you, it's not. The answer to both is hiding in the same special group of elements.
And here they are. Meet the heroes of our story today. The D block elements, or as you probably know them, the transition metals. These are the elements that are doing all the heavy lifting, creating those incredible colors and powerful magnetic fields we were just talking about.
So what officially makes a metal a transition metal? Well, the technical answer is that it's all about where its very last electron decides to live. For these guys, it's in a place called the d orbital. But a much easier way to think about them is to look at where they sit on the periodic table. They literally form a bridge that connects the superreactive metals on the left side with the nonmetals over on the right.
Okay, so what's their secret? How do they do all this cool stuff? Well, it all boils down to their electrons. The real key, the master secret to everything that makes them special, is hidden in their electron configuration. That's just the fancy term for how their electrons are arranged. So let's get into it.
Generally speaking, their electron setup follows this formula. Now I know that looks a little complicated, but all it's really saying is that electrons tend to fill up the outer energy level before they start filling up the one just inside it. But here's the fun part. Some elements are total rule breakers.
Let's take a look at chromium. If you just follow the rules, its configuration should be 3d4, 4s2, but it's not. In the real world, it's actually 3d5, 4s1. So what's going on? Well, it turns out that nature absolutely loves stability, and having a d orbital that's exactly half full or completely full is like hitting a stability jackpot. So to get to that perfectly balanced, super stable state, an electron actually promotes itself. It makes a little jump from the 4s orbital over to the 3d orbital. Pretty clever, huh?
And that one little fact, that unique electron setup, is what kicks off a massive domino effect. It's the one thing that explains pretty much all of their famous properties, from their colors to their magnetic pull. You see, in chemistry, one thing always leads to another.
So first up, they can have a bunch of different oxidation states. Here's a way to think about it. Imagine the outer ends and the inner d orbitals are like two floors of a building. Now for these metals, the staircase between those two floors is super short. The energy gap is tiny. That means electrons can easily be used for chemical bonds from both floors, not just the top one. And that's why these elements are so incredibly versatile, showing off states like +2, +3, all the way up to a whopping +7 for manganese.
And now we can finally answer that question about color. When plain old white light, which has all the colors of the rainbow in it, hits one of these metal ions, one of its d electrons gets all excited. It soaks up the energy from just one specific color in that light and uses it to jump up to a higher energy level. We don't see the color that gets absorbed. What our eyes see is everything that's left over, the complementary color. Basically, the element eats one color from the buffet of light, and we see the beautiful color it left on the plate. And there's a really simple rule for this to happen. The d subshell has to be incomplete. It can't be empty, and it can't be totally full. And this is exactly why ions like scandium, which has 0 d electrons, or zinc, which has a full set of 10, are both colorless. Think about it. Scandium has no electrons available to make the jump, and zinc has no empty parking spots for an electron to jump into. No jump means no color. It's that simple.
So what about their magnetism? Yep, you guessed it. It's another electron story. When an ion has unpaired electrons, electrons that are just sitting all by themselves in their little orbital rooms, each one of those lonely electrons acts like a teeny tiny magnet. And when you have a bunch of them, the whole substance gets pulled in by a magnetic field. We call that property paramagnetism.
All of this brings us to another one of their amazing superpowers. They make incredible catalysts. Because they can have all those different oxidation states, they're champs at speeding up chemical reactions without getting used up themselves. That's why metals like iron and platinum are absolute workhorses in the chemical industry. They make everything from the fertilizer that grows our food to the plastics we use every day.
Okay, let's see how this all plays out in the real world.
A perfect example is making potassium dichromate, which is a really strong chemical agent. You start with something called chromite ore. First, you roast that ore with an alkali, and you get this yellow stuff, sodium chromate. Then, you add some acid and watch the magic. The solution turns from yellow to this amazing, vibrant orange. That's your sodium dichromate. And for the final step, you add some potassium chloride, and these brilliant orange crystals of potassium dichromate just start to form.
So we've gotten to know the D block pretty well. Now let's meet their extended family, the ones kind of tucked away at the very bottom of the periodic table, the F block elements. They're also called the inner transition series, and trust me, they have their own set of weird and wonderful rules.
So here's their most famous and frankly strangest feature. It's called the Lanthanide contraction. Now normally you'd think that as you add more protons and electrons to an atom, it's got to get bigger, right? Well, for the lanthanoids, the exact opposite happens. As you go across the row, the atoms actually get smaller. This happens because their inner F electrons are just terrible at shielding the outer electrons from the nucleus's pull. You can imagine it like a great atomic squeeze, where the nucleus just keeps reeling those outer electrons in tighter and tighter.
And this atomic squeeze isn't just a quirky fact. It has huge, real-world consequences. Because of it, elements in the row right below them, like zirconium and hafnium, end up being almost the exact same size. They become chemical twins, which makes them incredibly difficult to tell apart and separate from each other in nature.
Now the F block is actually split into two different series. You have the lanthanoids, and right below them, the actinoids. They have some things in common, but there are some really big differences. Lanthanoids, for example, pretty much just stick to a +3 oxidation state. Actinoids, on the other hand, show a much wider range of states. But the biggest difference? Every single actinoid is radioactive. And they also have an even stronger size contraction than the lanthanoids do.
So we've covered a lot of ground. Amazing colors, powerful magnets, shrinking atoms, industrial powerhouses. So, after all that, what's the one big idea you should walk away with? It's that the root cause for all of these complex, fascinating properties boils down to one simple thing: the unique way their electrons are arranged.
Exactly. The behavior of these elements isn't just some random fluke of nature. It is a direct, predictable result of their electron structure. Everything, from the color of a ruby to how a factory makes a chemical, depends entirely on how those tiny little electrons are organized.
So now that you're in on the secret, start looking around you. Where else do you see these special elements at work in your everyday life? I guarantee you'll start seeing them everywhere, from the pigments in paint to the special metal alloys in your phone and in the buildings all around us. Their magic really is everywhere. Thanks for watching, and until next time, keep asking questions.